All right. Hello, everyone, and welcome. Thank you for choosing to spend your valuable time with us. Today's webinar will cover wolfHSM, automotive hardware security modules, functionality, design, and applications, presented by wolfSSL software engineer Bill Phipps. My name is Emma, and I will be moderating the webinar. All attendees will be in listen-only mode, and if you have any questions, please use the Q&A box. After the presentation, Bill will answer any questions, and as always, all of our webinars are recorded and made available on our YouTube channel. If you'd like to stay updated with the latest from wolfSSL, follow us on Twitter, connect with us on LinkedIn, and subscribe to our YouTube channel. Feel free to reach out to us via email at facts@wolfSSL if you have any further questions. Before we dive into the technical presentation, I'd like to provide a brief overview of wolfSSL. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL consists of over 50 dedicated employees, primarily engineers, and this progress is of course supported by a strong partner network that we are very proud of. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO178 support, a FIPS 140-3 certification, and a FIPS-ready offering, MQTT up to the V5 specification, SSH v2, TPM 2.0, a secure bootloader known as wolfBoot, Java wrappers and JSSC support, and commercial support for curl, and our newest product offering, wolfHSM. These offerings are accompanied by thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. Before we dive into today's topic, I'd like to share an exciting event we will also be attending soon. wolfSSL will be at SCAR Europe in Dortmund, Germany. SCAR Europe is happening on November 19th and 20th. Be sure to visit us at booth number 7 to discuss our latest innovations. Now I would like to turn it over to Bill to discuss wolfHSM, automotive hardware security, modules, functionality, design, and applications.
Thank you, Emma. Good afternoon, everyone. Thanks again for joining us. Again, this is talking about wolfHSM, and we'll be focusing mostly on the automotive space, but the security solutions that HSMs can provide can be used for aerospace, medical, communications, a lot of other vertical markets as well. So some of these techniques that you'll see within here are equally applicable to other areas, not just automotive. I'm going to walk through some of the design of what we put together with wolfHSM, taking a look at what the market was, talk about how these things match what you need to accomplish in a cybersecurity solution for automotive. We'll work through how we support porting to multiple hardware, and then I'll provide a demo on 2 different Aurix tri-core boards just to kind of demonstrate how this works in real time. So let's start at the very beginning. What is a hardware security module? From our perspective, we see an HSM as a protected and separate execution context. Usually it is a dedicated hardware core. In addition, that works in context with a series of application cores. This connection between the two is generally a shared memory solution, but you'll see what we've done is we've abstracted that transport layer to support the idea of a hardware security module in much different types of embodiments as well. The concept of the HSM is because it's separate, it normally has exclusive access to system level types of security things that you would say enable or disable debug, you would handle maybe tamper events. And likewise, there's normally some hardware cryptography offload that you're able to do along with some secure storage. The HSM core normally has access to environmental monitoring so that you can see if you're in the environment you expect. Maybe it's a temperature attack someone's doing, maybe someone's disconnected some pieces. So normally the HSM core has access to detect things like that. But at the end of the day, the HSM is more of a toolbox. It is not an overall solution. And so it's really up to you as the user to see what you can do with the tools the vendors have given you and wrap that around your overall cybersecurity solution. So at the end of the day, what we're finding in the market today is it's a toolbox. It's a DIY type of solution. How does this compare with some other existing solutions that are out there? So I kind of threw up here TPMs versus HSMs versus a virtualization or a trust zone. A TPM, trusted platform module, This is a separate device, a separate spec, but it operates differently. It is not user programmable at all. It's something that you can talk to, but you can't install your own code onto it, and that's distinct from an HSM and likewise from a virtualized solution or a trust zone solution where you can put your own code in there and have it execute custom functions for you. TPMs generally are not tightly coupled. Sure, you can see low pin count buses, SPI buses as they interact with that, and you might have some hardware support to try to protect address space. But at the end of the day, the TPM is a separate device from your main application cores. So it's not tightly coupled as opposed to HSMs and trust zone solutions, which are. I mean, they literally execute in the same memory spaces and as your applications. TPMs do provide hardware cryptos. Most HSMs have hardware cryptography, but I'll claim it's partial. You'll find only certain algorithms are installed or supported in hardware. And so it's up to you as a software developer to fill in the blanks. From a trust zone or virtualization perspective, there's no implicit hardware crypto. You might be on a platform that the CPU maybe has some intrinsics that can help out, but generally there's not a dedicated hardware engine solution. From a physical protection perspective, TPMs absolutely provide physical protection. Most of them are, you can get to a level 2 or level 3 in a FIPS compliance perspective. HSMs generally have physical protection. Trust zone virtualization, I put as partial because it really doesn't give you that physical protection. Yes, you might have some bus lines that are protected due to addresses, but at the end of the day, there's no physical way that a virtualization solution can actually protect you. Non-volatile storage, this is again where TPMs do provide a limited amount of non-volatile storage. Most HSMs do provide non-volatile storage access to the main non-volatile storage, as well as typically a separate non-volatile storage that's exclusive to the HSM or can be made exclusive to just the HSM module. Trust zone virtualization, this is a big problem. There is no defined way of doing non-volatile storage. In fact, if you take a look at some of the trust zone solutions that are out there, they require a running operating system to gain access to NVM. It's in one of the, like a hypervisor type of solution. So it's a miss in terms of that implementation. From a tamper response perspective, a TPM can do part of it because it's not tightly coupled. It can only protect itself. It can't necessarily let you know that, hey, there's been a tamper event if someone cuts those lines. HSMs typically are tightly wound to the rest of the system. And likewise, trust zone virtualization doesn't really have a concept of tamper response because they're designed to not necessarily sit on the hardware directly. So from that perspective, you kind of see the what I would claim is a rainbow of solutions, a spectrum, if you will, between a separate physical solution and a integrated solution with an HSM and a totally virtualized solution that doesn't really rely on hardware with the trust zone or a virtualized solution. So this is kind of the scheme where we see HSMs sitting. From our perspective, we believe that an automotive HSM has some functional requirements. It needs to be involved in the secure boot of the ECU. It has to be able to authenticate certain critical code sections, maybe not all of it, but it has to be able to at least authenticate itself and the initial boot sections of the applications. It needs to support in-system updates and then ensure that you can't roll back. So these are just some of the basic secure boot features. It needs to be able to protect calibration or configuration data that the application has. And so that means maybe not all of that data is stored in the HSM private, but perhaps maybe the keys that are used to protect the storage of the configuration data are stored in the HSM alone. It needs to provide certain cryptographic operations to support runtime cybersecurity. This is obviously key storage for both private and secure symmetric keys. And it needs to support obviously encryptions, hashes, and signature algorithms. This is the idea here is that if you offload that to the HSM, you kind of get a twofold benefit. You're knowing it's executing in a secure space. You're knowing that that hardware is usually set up with some countermeasures to support things like differential power analysis attacks to you. And the second thing is this is code that's not running in your main application space. You've literally just offloaded that, and you can regain some time back as that cryptographic operation is going on. You need the ability, this is again features of an HSM, to enable and disable debug and test interfaces and detect when people are trying to attack those debug and test interfaces and potentially take a response to that. need to support the life cycle of the system, all the way up into and supporting failure analysis modes. And that's really where some of these HSMs have a lot of support, or at least the chip software has a lot of support to support, post-mortem analysis. And at the end of the day, obviously, there needs to be some real-time and safety critical requirements that you need to be aware of to support inside the secure unit as well. So with those in mind, we took a look and said, hey, this is likely how we would logically break apart an HSM or a secure solution. A lot of times when you deal with cybersecurity, you deal with boundaries. And so what we found in the market is a number of systems that match this type of design, where you've got on the left-hand side, you've got a secure area, which has a dedicated core, which has access to cryptographic acceleration, as well as some of these what I call custom controls. This would be like enabling, disabling debug interfaces and things like that. Normally, the HSMs operate out of a local dedicated RAM space where software that you've got loaded is enough software to do like a bare metal boot of the core and then perform serving roles. So you can service requests from the applications. Likewise, most HSMs have dedicated flash where we can store private key material, which is protected in a different fashion than the main flash. So from the secure area, logically, we're combining a set of hardware-specific components, RAM that's running software that we control, and then likewise dedicated flash. This is connected to the non-secure area, which we have multiple cores connected through some potentially shared bus or really anything else that can do that. And the important aspects here is that the HSM core has access not only to communication buffers that are shared amongst the cores, but as well as to the main flash. So it's able to measure images that these cores may be running. On each of the cores, you would normally have your normal user app and then some sort of library that would connect back through this communication buffer to issue requests to the HSM core, who would then issue responses back to you. So logically, that's the way we've broken this out, and we say, hey, this is a valid model for not only multi-core chips, but also multiple chips on an environment or on a board that maybe is connected via a serial bus or a network bus or something like that. So the same logical diagram can be used for multiple hardware instances. The reason we got into HSMs is we had a lot of our customers who were working on automotive solutions, and they ended up needing to gain access to the HSMs. And so we've been doing consulting work for a long time in this space. Our wolfSSL and wolfCrypt products are already in many automotive products. And so we're used to doing this type of work. Some of the key features here is the fact that we do already support hardware offload. And so being able to offload to an HSM is just a natural extension of our existing software solution. Our wolfBoot product, which Emma mentioned earlier, does support bare metal bootstraps, and it does support fail-safe updates in place. And so these are features that we know HSMs have to have. So, hey, we're already doing part of that work. Let's see if we can port it to those hardware platforms that we've got customers interested in. We also support secure boot, either vendor-supported features or doing measured boot through our own cryptographic operations with wolfBoot. So these types of features we're already solving. We have access to things like wolfTPM and our crypto callback. This is how we do abstracted hardware cryptographic interfaces. We're used to doing this. We've ported many different hardware platforms to work within wolfCrypt seamlessly so that the user code simply writes cryptography code and wolfCrypt figures out which hardware device can do the work for us. Support for wolf PKCS11. This allows us to act as a PKCS11 responder, which means that if someone has already code written and that uses PKCS11, they can simply point to our library, and then we can use that to pass those calls on to wolfCrypt or to wolfHSM so that the customer can jump into this a lot faster. The other big thing that we wanted to make sure was clear is that because the hardware vendors tend to have to be behind in terms of which algorithms they're implementing in hardware, we support the latest algorithmic advances, specifically with post-quantum. We're one of the first companies that are out there pushing CNSA 2.0 and post-quantum solutions. We support ARIA, Shangmi ciphers. So this is where that algorithm agility that our software can bring to the table really helps out. And this allows you to fill in depending, regardless of what hardware you're on, we can fill it in with secure ciphers that meet your customers' requirements. And again, we obviously support NIST and FIPS compliant, but we also support non-NIST crypto if you need to get your product into a market that needs a different suite, or you just need to move forward with post-quantum. We have full support of that, which means any hardware you can see, we can run our post-quantum on it. From our perspective, one of the big things that we wanted to make sure happened with our HSM product was that it's open source for both the server and the client. Now, some of our hardware vendors still have NDAs required to do the interfacing to their hardware-specific stuff, and we handle that the correct way. The point, though, is to make sure that you as a customer, when you're using our products, you get full access to the source code, which means you're able to tailor in and out exactly the features and functions you want. You don't end up with a bunch of code that maybe comes to you as a chunk of code that you can't get rid of. So everything we have is designed to be modular. This also means that we can fill in those missing hardware functions. If you need to, let's say, I'll pick on the Tricore Aurix platform. It can't support RSA of large keys inside hardware, so we fill that in with software. So it's from your code perspective, you write it once, whether you're on a Tricore or an ST part or somewhere else, it doesn't matter. We'll implement that function for you. We also wanted to make sure we could maintain a common API for whether it was software or hardware. So this abstraction to wolfCrypt allows us to fire off those functions to the specific hardware without you having to change your code. So this also gives you that flexibility to not have any vendor lock-in on the hardware, and you're simply using these common APIs that you may have already been using in software. In fact, we're going to give you some examples of how the code changes, but now you get the advantage of being able to execute in hardware and control both sides of the conversation. Again, you get a chance to modify the server code as well as the client code. We want to ensure, obviously, asynchronous operations, static memory allocation, no system libraries in the servers if you needed to. So these are, again, from an embedded perspective, these are the features that we saw as critical to doing that. The last piece I wanted to point out is we wanted to make sure that you always had a simulator that was available that you can run on your desktop. So even when you don't have hardware, you can still work out the rest of your logic on the cryptographic side to ensure that when you do move your code to the hardware, it's going to work the way you expect it to go. At the end of the day, user extensibility was the key feature we wanted to make sure. We wanted to make sure that whatever you wanted to accomplish in your HSM and secure space, you could get done without having to reinvent the wheel. And this is why we made things modular and extensible, and you can register custom callbacks and things like that. So functionally, we broke this onto two different pieces. Obviously, an HSM client library, where we provide you a customized version of wolfCrypt. And again, this has been ported to whatever your application core's architecture happens to be. Optimize, assembly if necessary. And then we added in the HSM server as an offload. So as you're writing your application code, you can select to run the cryptographic operations locally or to the HSM just by toggling one of the initialization setup parameters. Again, this is done with the communication interface that's a request response type of solution. And we support different key management, different non-volatile memory management things. Again, that's what's also different is access to storage inside the HSM. We wanted to make sure that was exposed to the client. And then we support, obviously, automotive specific protocols like the SHE protocol. On the server side perspective, we start off we use wolfboot to boot up the server. We then gain access to the NVM so we can extract our local configuration. There is a second instance of wolfCrypt running. Now, this is specific to the HSM's core architecture, so that has been optimized likely very differently and likely has different features. In the example, I'll show you how we tailored out certain features on the core, on the client, and only gave it to the server to do that. From our perspective in the server, we do crypto offload to the hardware that's now accessible to the HSM core, and then service those requests coming in from the client. Obviously, we support security controls that the HSM has to take care of. We do support an image manager, so we can provide a measured chain of trust as your applications boot. The HSM server can measure that application, generate the measurement, and then verify that's the right one using, again, keys that maybe it only has access to. So Logically, this is kind of what it looks like. So at the end of the day, your system level software is you're going to have some user level application that has this client API. It's going to communicate to your server in some port specific fashion. Now, this is where our porting becomes important. Your application is almost entirely written without knowledge of how the porting actually works, because it's just saying, hey, issue a request, get a response. It's the client library takes care of translating that to whatever medium transport that you need to get the data to the server, and then bring it there back. Likewise, the HSM server application, it runs mostly agnostic of hardware except for handling incoming communications, and then whatever the hardware engine offload that we've got tied into. Aside from that, it operates generally in a platform agnostic solution as well. This allows you to move your server code between different servers as necessary. The client library itself, again, is broken up into a couple different pieces. It has a non-volatile memory manager, which basically routes non-volatile calls to the HSM. It has a key manager, which it can manage local keys as well as have access to HSM provided keys, or keys that only exist on the HSM itself. And then it has a full instance of wolfCrypt that can do whatever software crypto you want to have. Again, any algorithm that you want to compile into your application, you can do it and execute locally, or it can offload to the crypto client. The only things that are necessarily port specific are how we communicate with the HSM, and which is through flags, generally, which drive interrupts, as well as through a communication buffer, which again generally is in a shared memory space that you set the addresses up to protect. So that's roughly how the client library is set up. And again, it's very, very few port specific items there. From a server perspective, the overall server does a bare metal boot. It walks through the image manager to make sure the application cores have the load they want. And again, this is modular, so you can add and subtract whatever pieces you want into the boot sequence, and then it jumps into a server role where simply looking for new requests coming in from any of the cores, so that can service those. And each core has its own communication context, its own set of dedicated memory, so that the cores don't necessarily impact each other when the server is executing requests for them. From the Wolf Server's API, obviously you've got access to the non-volatile memory manager, which gains you access to your local HSM flash as well as to main flash. And again, these are marked blue, so they're port specific. This is where when we port to a new hardware, we provide these libraries back to you. Some of these are provided by the vendor. Other times it's just register interfaces that we wrap inside API calls. There's a key manager interface. And again, there's usually hardware crypto keys that we have to expose and abstract out to gain access to them. And then likewise, there's a hardware crypto acceleration module that's port specific as well. So from a server perspective, it's just a straightforward application that boots up, configures everything, handles all of these additional controls to make sure that the system's in the state that it's supposed to be, handles interrupts for tamper events and things like that, and you can trigger whatever response you'd like to have. It might be to erase all the memory or something like that, and likewise handle communications with the clients as well. So from an AUTOSAR crypto stack perspective, from the client side, we do expect that many of our customers will use an AUTOSAR operating system and stack to talk to us. So we have been used for many years within crypto drivers themselves, and we do believe that because we're asynchronous, because we've abstracted, because it's a layered solution, this does match the way AUTOSAR expects crypto drivers to look. One of the things that we wanted to point out is that the AUTOSAR crypto stack has certain limitations in how it does that. And so it limits what you have to do. So let's say you have a sequence of calls that you always execute in the same sequence. From an AUTOSAR perspective, you'd have to do each of those calls sequentially in the user. But from our perspective, you could set up a brand new function, ask the server to do this sequence of functions for you, and then get a single response back. And so that extensibility changes the way you can use this. So although, yes, we certainly support AUTOSAR, and we actually will be putting together our own crypto driver specific for the HSM. For AUTOSAR, that limitation of how you do these things and taking advantage of what an HSM can do with custom code, I think you can see it can add some new features without necessarily breaking AUTOSAR compatibility. I'm going to walk through a couple of these things. I'm going to get to some software examples so you can see how this goes. These are just some APIs. So let me walk through one software example. On the left-hand side, this is pure wolfCrypt function. And in this case, we're simply going to do an encryption. We're going to do an AES CBC. We want to encrypt it. And so from this code example, we've got some key material that we have the actual keys that are saying there. We've got some initialization vector that we've got. Our normal sequence was you would initialize an AES context. In this case, we're pointing it to an invalid device ID, which says use software crypto. We don't have any hardware to offload it to in this case. So once the AES context is initialized, we set the key and the initialization value. We have the entire key material. We have the IV, and we set the direction of this AES to be an encryption as opposed to decryption. Then we invoke this AES CBC encrypt using that context we've pre-configured with the key. Here's my my plain text in, ciphertext out, and then we would free that up. So this is exactly the sequence of commands with a wolfCrypt only solution. We're going to switch this up now. We're going to show what you would change if you wanted to do this the same sequence with an HSM solution. In this case, we're going to make the example that instead of knowing the key up front, all we know is there's a key identifier that the server knows. And this is just some fixed constant that we've preloaded that key into the server. Same exact code here, except this time when you initialize the context, you initialize it as a wolfHSM device. So now your client knows, hey, when I invoke the next sequence of commands on that context, it's going to go to the HSM as a request response. A new function, which is to set the AES key as a client, or say, hey, associate with this context, associate this key ID value. Now remember, I don't have the actual key values. We just have the key ID with this context. Then we set the IV separately, which is just a split up of this set key function. And then we invoke the exact same function, AES CBC encrypt on that context, and then AES free at the end. So what this does is this allows us with a handful of calls. We've simply modified the key material, the initialization call, and how to set the key material before we've done any of this. This is, again, it would likely be in a constructor somewhere where you'd set these things up. The rest of the information is exactly the same text, exactly the same code, which is kind of the point. We wanted to make sure that the API to use an HSM was very, very similar to the API that you would use in a pure software environment. This is a second example where we're going to have similar information, but we want to store a key material into the server so it can use it after the fact. So in this case, you're still going to have the key material. The left is the same code that you saw previously. This time, instead of knowing the key ID, we're going to use it to an invalid key ID. So when we go to store that key, the server will pick a unique key ID for us to use and let us know what that key ID is. So this time we do have the key material, but we don't want to do the operation ourselves. We want to offload this operation. Again, initialize the context. We pass through the device ID for wolfHSM. This, again, tells wolfCrypt to pass off upcoming AES calls to the HSM itself. At this point, we now cache this key, which is the ask saying, hey, I've got key material that I want you to store, and I want you to use this key material, for future calls. So now it'll be held in RAM on the server. It won't be necessarily stored to NVM, but there's a couple other calls that can convert a cached key to NVM, so you can extract it next time. But in this case, we're simply going to store it into the server's RAM for this context of the client, so that we can use that key and have the server do all the work for us. So this key cache basically takes that key and the size of the key and says, hey, put the answer, what key ID you stored it in, back into my key ID. Then we simply set the same context with that key ID that we got back from caching the key, and invoke the same sequence of events afterwards. And the only thing that's different now is because, remember, we have stored that key into the server's RAM. This key evict says, hey, server, I no longer need that key. But this is how you would handle placing a key into the server context and have the server use that key. So it's the same type of idea, but again, this is user supplied key material. Imagine you get this key material, let's say through a TLS key establishment method. That's how you would get the stuff, and this is how you would pass that stuff off to the server. So just a couple of code examples of how to do that. I'm going to skip through some of these NVM pieces just because we've got that. Let me walk on to some porting. So when we talk about porting to new hardware, and again, these slides are available via PDF, and Emma can send this to you on demand. That's not a problem. So you're not really missing anything. I'm just going through some of the mechanics of how we handle non-volatile memory. From a porting perspective, what we saw that was important was that you would really have two different phases. You would start on the left-hand side on just a standard development box using our POSIX port. This allows you to work out all of the mechanics, the sequences, including the custom calls that you had, as long as it didn't hit custom hardware, to be able to stub out all that functionality and then prove that things are working. We also use our POSIX port to perform unit tests, so that if I have a sequence of known goods and known bad inputs, I can drive those through my applications on my desktop host without ever even having the hardware to prove that the software is correct. So from our client perspective, we simply configured our bottom end hardware abstraction to be the POSIX communication port. Now that can be like a TCP connection, it can be a shared memory connection, it can be multiple threads in the same application, one thread acting as a server, one thread acting as a client. All of those are fully supported in our POSIX environment, again, depending on how you wanted to code things up. And again, this is what we started with, is just the POSIX port. You work through your custom functionality, you get it all working the way you like it to, and then you can move it over to your embedded target. Now, the only thing that's fundamentally different is there's a set of configuration values that you would pass to say, here's the callback functions to communicate with my server. Here's the callback functions to talk to specific hardware for non-volatile memory or to do hardware crypto. And so your server application then gets rebuilt, but this time it gets built with the proper hardware engine. Your client library gets rebuilt, this time with the proper hardware abstraction at the bottom end, but the overall applications don't change. You're still invoking the wolfHSM setup sequences. You're still invoking the wolfCrypt functions the exact same way. So this gives you an opportunity to not only work out the main development, but also give you a testing solution. So that way you can always unit test your stuff on your desktop or inside. We hook that into our GitHub actions. So whenever we commit a new change to wolfCrypt or sorry, to wolfHSM, we trigger a whole sequence of tests that use the POSIX simulator to prove that we didn't break our existing API. Ports that we're currently working on, obviously we've got, we just released our Aurix TC3 series, and it supports, all the features of the Aurix platform from an HSM perspective, as well as this provides you an optimized tri-core implementation as well. The examples I'll be showing today use this port on two different kinds of tri-core 3s. We also support the ST-SPC58N series, which is, again, it's PowerPC based. It has another HSM core that's a slightly different model than the main model or the main application cores, and has a limited amount of crypto offload just because that's the way the hardware was set up. I did want to also point out the Aurix platform is fun because the application cores are one architecture. It's a tri-core application or architecture, but the HSM core is actually a standard ARM Cortex M3. So this you have to be able to handle those different architecture pieces and communicate correctly. So that was a fun port for us to put together. That's on there. What ports have to do? Ports have to implement specific hardware interfaces. Again, this is access to non-volatile memory. We have extraction libraries that if you have flash-like devices, then you can easily lay our libraries on top of those to support object management. So we provide persistence and fail-safe reads and writes of objects to things that look like Flash. So if your devices have a read, erase, program, maybe a blank check function, you can simply invoke those functions directly as a what we call a how flash layer. If it's something more unique, then you'd have to create the overall non-volatile memory object management calls directly. But again, we've got examples of those. Even we have a POSIX simulator that the function calls that go down look like read erase program, even though they simply map to file reads and writes on the POSIX simulator side. So ports also have to provide any crypto hardware interface. Normally, this is a true random number generator, access to any keys, specifically any unique keys that are baked into the hardware, and then access to symmetric and asymmetric crypto. This is normally how things work. Normally, these are either register interfaces, or sometimes you get a small library that you can link into your server to gain access to these to do that. So ordinarily, we are simply mapping a crypto callback, a wolf crypto callback series of interfaces down to the cryptographic hardware. From a platform interface, the wolfHSM server has got to understand the boot sequence, how to control the application core resets, and then likewise, how it interfaces with memory. You'll find, again, I'll pick on the Aurix because we got demos of it. Although the HSM can have access to any piece of memory in the Aurix system, how it does that sometimes is challenging because it only has a single window, 64K at a time, that it can map to gain access to those different pieces of memory. So if you're asking the HSM server to, let's say, touch a peripheral and then touch some user space, that turns that into a sequence of calls where I've got to update the window, touch the peripheral, update the window, touch the user space memory. And so it's definitely a sequence. So from the porting perspective, you need to be aware of what memory limitations you have and how you need to handle those within coding. You also find things like memory fences and caching, memory caches and explicit cache invalidations and cache flushes are necessary. And so these are things, as you go to do a hardware port, you need to be aware of how those things go. Again, the specific port and the configuration of that port are selected at compile time. So you might see a library that, we've got a lot of different hardware interfaces on there, but you select the one at compile time the way you want to use it. Generally, things like memory locations are, you compile in a hard-coded address that you want to use for, let's say, your shared memory communication buffers. But you can also modify these. The libraries themselves can be modified at runtime. So you can pass in, oh, hey, this is the configuration address I want to use. He just mallocked a piece of memory, and I want to use that chunk of memory. And so even some of our test cases handle that specifically for the POSIX side. So from a configuration example, this is an example of how we set up our hardware abstractions. And so when I say it's configured at compile time, this is what the code actually looks like. So in this case, I'm giving an example of I'd like to implement an NVM store using a Flash backend. We're using the Flash hardware abstraction layer. So this is the API for that. And the last is I'm going to use a POSIX style, and this is using a file system as a backing store for the Flash. And so this interface provides an implementation of the Flash that uses a file in the bottom end. First, by kind of working backwards, we say, hey, our Flash callbacks are going to be our POSIX Flash file callbacks. Again, this is just a defined struct that has a series of function callbacks in it that's within this POSIX Flash file. I then provide a context to use at runtime. So you've got it split between dynamic context. So this is keeping track of the state of that object at runtime versus the configuration of that object at compile time. And then, so this is that context. We combine that together to provide an overall configuration, which says, oh, hey, for this Flash file configuration, I need this one requires a file name and maybe a size. And then maybe in this case, what we're doing is when we erase a byte, what value does it have? And so this is configuring that POSIX Flash file configuration. This is the context we'll use with that. And this is the callbacks that would use both the configuration and that context at runtime to know how to do those. This entire Flash callback, you simply combine into here and say, oh, the callback I want you to use is this group of functions, which provide the read, the erase, the program. The context, this is the dynamic context, and which config do you have? So these are all, again, set, in this case, are just set statically, but there's nothing stopping me from, let's say, taking the file name in as an argument, updating the configuration value, and then passing that in to initialize this. So we do this with all of our different hardware abstractions, is you have these structures that combine context and configuration with callbacks to make sure that you can swap out the bottom end. The rest of your code doesn't change. So our code would say, hey, initialize, a Flash or an NVM instance using this Flash config, and then boom, you're off to the races. You can use that. So this is just as an example of how we handle configuring things either at compile time or at runtime and into this layered solution. So let me jump into a couple demos. I think I have plenty of time to do this. So I'm going to work through two different demos. This first one, this is on a tri-core 367 DP. This is a dual core tri-core. It's got a The HSM cores are the same on the Tri-Core 3 series. And the Tri-Core supports, the hardware does support RNG, AES-128, ECD-ESA, at 25519, as well as SHA offloads. What we're going to do in this sequence is we're going to walk through bringing up the Tri-Core. The Tri-Core is the only thing that can talk to the serial port. So it's going to not only print out its own statements, but it's going to collect statements from the server and print those out as well. We're going to establish comms to the HSM. Then we're going to walk through on the Tri-Core side our standard wolfCrypt test. Now, the wolfCrypt test is our standard known answer test that we go through every application or every algo that we've compiled into the wolfCrypt library and hit it for positive and negative results to make sure that all of the crypto is working correctly. Again, these are known answer tests. So if we get the wrong answer, we stop the test and say, hey, something's broken on your hardware or in the implementation. And the second thing we do on the Tri-Core side is we run a benchmark, which we run each of those algorithms for about a second and then capture how much data we were able to process through those. Again, this benchmark and test programs, these are our standard unmodified test and benchmark programs. They've simply been ported, compiled to work for this. The second thing we do is that's all executing on the local application Tri-Core. The next thing we do is we ask the ARM chip to do the exact same sequence of tests. Run through your wolfCrypt test, but this time on that Cortex-M3, and then run through the benchmark also on that Cortex-M3, and simply dump the results back to us. After that, we walk through a couple of low-level functionality tests just to prove that we can hit the crypto hardware correctly from the HSM's perspective, generate TRNG. We execute a couple of custom callback function tests, and then we walk through all of the rest of the hardware crypto tests to prove that all of the hardware is working and doing simple known answer tests. So that's what this demo looks like. Logically, this is the way this system maps to the same picture that you saw. We have a simple bootloader that's running on the HSM server side. It listens to requests. The user app is pretty simple. We're only running this test off of Core 0. Core 1 is simply in a user app that spins. It has an HSM client library that issues those requests through a shared memory buffer. The HSM then has access to the crypto to do that. In this case, the wolfCrypt test will be running locally on the core and then locally be running benchmark, and then it's going to ask the HSM core to do the same thing, locally run the test, locally run the benchmark. The only thing that's different than normal is that we have replaced printf to make sure that the HSM sends its outputs to a communication buffer, and then the Tri-Core sends it out to the serial port since we've only got the one serial port that's available. This Tri-Core app was built using the Aurix Dev Studio using GCC. So this is all off-the-shelf development environment. We're using the DApp libraries to update the Flash. The HSM app was built, we use the standard GCC ARM toolchain. So in terms of development environment, it's everything that is off the shelf and available to be downloaded. The wolfCrypt for the Tri-Core, we enabled our SP math library, which is an optimized version to support a large number computations for our crypto. And the wolfCrypt, in this case, we used our optimized assembly version of the Cortex-M library. So let me switch screens for a second, and I will pop up pop that guy up. Oops, where is he? All right, so I'm going to hit reset on this. This is again a 367, and it's going to walk through a sequence of crypto tests. Let me just scroll up and we'll walk through what it said initially. So right at the beginning. So we get the Tri-Core initialized, HSM initialized. This is the Tri-Core coming up. It announces over the serial port that it's working. The HSM comes up because we've communicated with the HSM, and the HSM then prints out, hey, we've initialized. Now we jump into the Tri-Core running the wolfCrypt tests. Now, the first thing that wolfCrypt does is it reports its version. So in this case, our Tri-Core is running wolfCrypt version or wolfSSL version 5.5, and it's been configured to do a sequence of different things. Again, the wolfCrypt tests every function that we have inside wolfCrypt. So it goes through things like you see the SHA test, SHA-1, you see the SHA-256, 384. It's just running known answer tests on all those things. So let me... It's getting into benchmark. Before I get there, let me get back up there so we can walk through that. So a couple of items I wanted to point out. You can see has AES GCM 256, AES 256 is supported. Again, remember the hardware support on the Aurix can't do AES 256, but obviously we do this in software. After it completes, it goes through and starts running. Again, this is only locally on the Tricore, a series of benchmarks. And I'm just going to we'll pick that AES 128 CBC encrypt. And you'll see we're getting about 3.7 megabytes per second. This is locally on the Tricore. Again, that's a 300 megahertz processor, plenty of cache. So that's a reasonable speed to see on that Tricore. So as we finish off, let me get back. So it finishes off. I'm going to point out a couple of other items here. So let's take a look at the ECC test. You'll see it's doing the prime 256 R1 curve for key generation, agree, and sign. Again, this is all running locally on the Tricore, but it's pointing out that it's able to do these calls locally, and you get a certain performance out of it. But it only invoked the prime 256 because that's what the configuration of wolfCrypt supported. It didn't support anything larger. Once we finish the benchmark, it then runs on to, it asks the HSM core to run the exact same set of tests and the exact same benchmarks. You'll see now these printfs are coming directly from the HSM core. You see we're running wolfSSL 5.6.3 in this case. So it's a different version of our wolfCrypt product that's running. You'll see we've got different levels of SHA supported. It was no longer SHA 512, only up to SHA 384. So we configured this differently than what we had previously. As we get into benchmarks, let's pick on that one number that we had last time. So the AES 128, the CBC, when we do this on a 100 megahertz Cortex, we see a much different performance. Now, this Cortex doesn't have a significant amount of RAM, nor does it have a significant amount of cache. So you see the performance running strictly in software on that slower Cortex is a lot less, so about 280K per second. And that's a reasonable number for a Cortex M. Again, it's a mobile series. It's not designed as an application as that performance. Again, that's just running in software on that ARM Cortex. But let me point out a couple other pieces. You'll see that when we came to do elliptic curve and crypto, you'll see the RSA now is up to 3072, whereas we'd only configured 2048 on the Tricore application side. ECC now, we added in prime 3D4 curves. So again, this allows us to segregate out which algorithms are running where. This server is now configured totally different from the client, but the client was still able to ask the question, hey, can you do a prime 3D4 for me? And the server said, sure, I'll do that. Now, the Tricore couldn't do it itself because it wasn't configured to support that. So as we walk through the rest of this test, it's just going through and proving out that we're getting, access to the random number generation and the hardware crypto that's available. I did want to show one last piece. So this was a quick test of AES CBC encrypt. It's a slightly different apples to oranges type of configuration from a buffer size perspective, but you'll see that when we offload that from the server to the hardware, we're right back up to that 3 megabytes per second. Now, if you take a look at the performance numbers that Infineon publishes, you can get a lot higher than this for much larger block sizes. But this was done as a small 256 byte block and run it a whole bunch of times. And so the point being is that when we offload what's hardware enabled, you get that performance back that maybe that slower HSM core couldn't pull off in software, but you do get that performance. So at the end of the day, what we wanted to show in this demo was that on that dual core 367, we can run two different versions of wolfSSL, wolfCrypt. We can have two different configurations. Things can communicate. We can pull debug information out. We can see the performance that comes out. And so from did we test everything correctly? Yes, all of the tests answered the known answers the correct way, and all of these hardware offload, they got the correct answer. And again, hardware offload is not go encrypt this thing for me. It is give me those intrinsics that help me compute that. So even these offloads are individual pieces. They're not full implementations of the crypto itself. It's just the building blocks toward that. All right, so let me move on to back to the other. So this is, again, just pointing things out. I'm going to continue on here. This was the same series of tests that I showed you. All right, let's move on. This is a second demo I've got. This is on a slightly different board. This is on a TC375 Dev Kit Lite. So it's a small, about $100 board that you can get out of DigiKey today. This has 3 application cores, so it's a one extra core that you've got access to it. But in this case, we're going to run a different set of tests. So the first demo was all low-leveled, can the hardware work? This one is actually a higher level test running as HSM clients and then issuing a series of custom callbacks and then do a couple of non-volatile memory calls to do that. The same setup in terms of how things are compiled and built is set up. Again, we've got a third core in this case, but the other two cores are doing nothing. We only have a single core issuing requests at this point. And this is what it's going to look like. So let me get back to that. This is in a second. So this is a 375. Let me hit the reset button right now. And this starts running a sequence of tests. Now, the reason I bring this test up is, oops, let me get down to the beginning of that. So this is the beginning of that. These tests that you see printing are the exact same tests we run on our POSIX simulator to do unit testing. So we just took our existing POSIX unit tests and then compiled and then put them onto the client specifically so that the client would then issue all of these questions. And so in this case, we walk through, we're setting up communication buffer. So we've got fixed addresses that it's talking to, our print buffer. We're now exposing and showing these things just for debug purposes. We do a handshake with the HSM to start off, which is what we expected. The first sequence, the first thing it asks it to do is to do a series of echo tests where it sends a message and expects to see the message that comes back. So this is just a request response proving that the communications are working. The next sequence, again, these are unit tests, so they're just dumping out information, has us insert a sequence of objects into non-volatile memory. It stores them securely, makes sure they're there, checks them, and then it retrieves them. Again, these are all unit tests that we do, and then it deletes those as we go back and ensures that, we ended up with the same amount of space that we started off with at the end of the day. Let me continue on through these NVM tests. Each time we do these tests, we are also comparing the data we got back to the data that we put in to verify that the server didn't mess anything up. We then destroy all of those things and we prove that we got all of our space back. Again, this is all done in a fail-safe fashion. The NVM ensures it's basically a journaled system where it ensures that those pieces are there. We then move on to a sequence of key management. We could do some requests to do an RNG, so we get a response back from that. We have a cache and export certain keys to verify that the key management sequence is working. We generate an RSA key halfway through there that the client never sees the private side, but the server does. And then we prove that it's working. And again, these are similar to known answer tests, but these are basically the same tests we run locally on our desktop. We run there. The last piece is that we gave the server 2 custom callbacks to execute. And so we register those callbacks and then we trigger those callbacks. This allows us to place custom code into the server and we just are testing that entire sequence. The point of the second demo is to show that we can take code that's compiled and or at least that's written to run for our POSIX simulator. We pick that code up, recompiled it, and simply changed the configuration. And everything worked exactly the way we expected on the actual hardware in the deployed environment. And again, that was all run on a TC375, about $100 out of DigiKey. So let me just click through the rest of these guys. So this was, at the end of the day, we're showing that yes, you can take this, you can start with this framework, the software framework that is the wolfHSM. You can work it through your POSIX simulator. You can then apply it to hardware that we provided the back end for, and the code works the way you'd expect. And again, all of the crypto that we have on any of our other platforms, we can port to those hardware pieces as well. And in terms of where we're going with this, we are actively working on an RH850 using the ICU-M, which is the separate space to work that. So we will be supporting the Renaissance series, obviously looking at the TC4 series from Infineon. And we have also are working just as a kind of a proof of concept to use a TPM as a back end. So you would still have an HSM interface, but it's using a TPM for the actual storage in the back end. We think there might be some application spaces that can't squeeze in a whole HSM, but can squeeze in a TPM. So this provides you that same software framework. We are continuing to expand our support for PKCS11 in the wolfHSM library. We are going to be adding in client-server encrypted communications, specifically when you're over a transport such as like TCP or UDP, where you don't have any intrinsic proof that the other person is who they say they are. So this adds in authenticated and confidential communications from the client and server. And then we are working a full AUTOSAR crypto driver for the wolfHSM product as well. There's some other features in the future from access controls and to give some examples of multi-session that we're bringing up there. So if you're interested, our main product page is listed there. All of the public code is wolfHSM off of GitHub. We do have a series of examples that kind of walk through, similar to what I just showed, how you can construct your own tests for this. And then we do provide build environments. We will be moving some of our Tricore examples over to there as well as we get permission from Infineon to share some of that information publicly. wolfSSL in general, our wolfCrypt source is also on GitHub. If you're curious about either wolfboot or wolfPKCS11, those are also sitting off of our GitHub website. So that's all I've got for today. I'll be happy to answer some questions now.
Perfect. We'll get moving on those questions. So what DO178C DAL levels have the different solutions been developed to?
So we did DAL A with wolfboot and wolfCrypt that actually had a TPM offload. So that was one of our customers. We have a second wolfboot with wolfCrypt in work right now that we're trimming off for a Tiger Lake environment. The wolfHSM product has not been brought through DAL A or any of those aerospace requirements yet. But wolfCrypt and the wolfSSL solutions, they've been through a number of other ones too. But if you've got some questions specific about DO178, I'll be happy to just send an email to facts@wolfSSL.com and we can get some more information about our DO178 support. We probably have some blogs on that as well. If you just search wolfSSL and DO178, we can probably walk through some of those existing solutions. Just as a heads up, just because we've done it once for one customer on a certain platform, DO178 is a system level approach. So almost, yes, there's certainly some lessons learned, but it's not like I can just hand you a validation package and say, oh yeah, this is going to work perfectly for you, unless you have 99% of the exact same environment as the previous one. Those certification packages are certainly tied to your end product. So you still will have work to do regardless of what we've already done. What I can say is that the lessons learned working through that process, we're in a good position to support a rapid and tight certification for DO178.
Perfect. What are the timescales for a TC4 implementation?
I'm sorry, you said what are the
Timescales for a TC4
timescales? Oh, how long it's going to take until we're there? That's
Correct.
a great question. Well, we just got our first TC4 in, I think, last month, and I'm not sure where that is. Generally, when we start a port off, we can get things up and running within a few months, and I'll say 2 months at that point. But it does take us probably another 2 months to finish off the build environments and the full test environments for that. So our porting time is generally about 4 months start to finish. Because the TC4 is in the same vein as the TC3, perhaps it'll be roughly that same time point, that same time scale to get that done. The TC4 does have some changes as it goes along. So even if we finish it off, there might be some changes that end up breaking what we put together. So depending on how quickly a customer needs it can help us prioritize that. So if you have a need for a TC4, again, feel free to reach out and help us understand what your timeline is, and we might be able to prioritize that, or at least get you a proof of concept of some of the functionality working on a TC4 to meet whatever timeline you've got. But generally, a port is about 4 months.
Thank you. How do you compare wolfHSM with other HSMs off the shelf in the market? What benefits does wolfHSM bring?
Well, right off the top, I would say we are starting with open source. This means that we don't deliver binary precompiled firmware to you. We're delivering source code to you, and so that puts you in the driver's seat in terms of your certifications. This also puts you in the driver's seat in terms of what features and functions you want to have included in there. So, being open source, really ensures that the customer is choosing exactly what the attack surface is and how you're going to what features and functions you're going to put in there. Cryptographic agility is another thing I definitely want to bring up. Our ability to bring in new algorithms as they're being approved with optimized implementations, I think is unmatched. I'll give an example. The NIST just released their updates to their MLChem algorithm, and the day they updated it, the very next day we had updates on our website that had those updates incorporated, including full unit tests. So our ability to stay on the cutting edge of cryptography and make sure that we're doing things absolutely the right way in an open source is definitely a differentiator. So from a crypto agility, you're in that position. And the last piece really is the extensibility. Because we deliver source code, but because we're delivering crypto callbacks in ways of extending the server without breaking the server to teach it new tricks that match what you want it to do. I think that's another distinguishing feature. So it allows you to group crypto callbacks together into atomic chunks that way your code, calling call can be a sequence of functions, which is likely. It's not likely you're going to do one encrypt operation and be done. No, you're going to be doing a hash, you're going to be doing an encrypt, you're going to be doing a verify. Those things always happen in the exact same sequence. So the ability to teach the server that custom sequence, compile that in, and then you trigger from a client side one function call that has, maybe 10 arguments or whatever it happens to be, you're done. So that extensibility, I think, also differentiates us from the other folks. Obviously, we are also taking a look at new hardware. So as customers come to us and say, hey, I've got a Xilinx system that I need to handle crypto in a totally different fashion between, the different cores and some fabric space. We say, hey, our framework looks like it could match that. It looks like you have a separate, quote unquote HSM secure area. So the framework we've set up works over different transports, things like TCP and serial lines. So it's not always just shared memory connections that you require DMA to work. These can work, as distinct separate pieces as well. So I guess from that perspective, our ability to handle updates to crypto, our ability to do custom callbacks and teach the server new functions, our transports agnostic stuff, so we can work on any hardware using any communication method, and then the fact that at the top of the page is all open source, and we're delivering source, not solution to you. I think that's what really differentiates us from other existing solutions.
Perfect. And then two last questions for you. To port into any specific hardware, what are all the components files to be modified or configured? Like, are there any porting manual integration, like manuals kind of?
Good question. Yeah. So so I think I mentioned this previously. You need to handle communications between the clients and the servers. So that's number one. Number two is non-volatile memory access. The server does require some piece of non-volatile memory that generally is platform specific. Number three, the hardware crypto. If the server has hardware crypto available to it, or if it has custom controls it has to handle for things like enabling, disabling debug, or handling lifecycle management, those would be need to be ported as well. We did start a skeleton program that says, here's in general what code you would need to add for callbacks, and then kind of fill in the blanks. And that's currently in the website or in our GitHub. But we do intend to provide a much more robust porting guide, and so you would just basically fill in the blanks of the skeleton with whatever functions that you had to get something operational from that perspective. From a Wolf server perspective or a Wolf HSM client perspective, those libraries are designed not to have to be changed based on the hardware. So let's say you wanted to use a shared memory transport. The shared memory transport expects that, oh, from one address I can write and the other side will see it, but there has callbacks to say, hey, how do you do memory fencing? What is the exact command? So you would provide that architecture specific memory fence command. We have some defaults that compilers usually like. So if you don't know that, you can use that as well. Likewise, for those, if you're moving that over a cache chunk of memory, we have callbacks to say, hey, how would I do a cache invalidate? How would I do a cache flush? And so you would simply register those callbacks in to handle that so that you could use it a generic memory transport if you put the proper cache flushing and cache invalidation instructions in there as well. So sometimes it's just as simple as putting in the right instructions as callbacks. Other times you have to write your own transport and then match the APIs that we've got there for you. But yeah, so the answer to your question is, yes, there's already a skeleton. I would definitely take a look at our examples for the POSIX TCP implementation as well as a shared memory implementation. Those are probably some pretty good examples of how those APIs would work. But we did expect to provide a kind of a skeleton program and a porting guide to kind of fill out that skeleton. That is not done yet, but that's on our roadmap of things to work on.
Perfect. And then last question here, with which version of AUTOSAR crypto modules is wolfHSM integrated and tested with so far?
So wolfHSM was just released, so I don't believe that anyone has actually finished off the full integration with AUTOSAR. wolfCrypt, on the other hand, has been placed into a number of different AUTOSAR solutions as the bottom end crypto. So I can go ahead and get you some more information about that, either the adaptive or the classic versus, or likewise the versions. But I'd say just go ahead and send an email to facts@wolfSSL.com. If you have a need to hear that question or get that question answered. Otherwise, we can take a look at, what if you're looking to do that on a certain AUTOSAR platform, we can help you port the wolfHSM and our AUTOSAR crypto driver to work with your specific implementation. But again, wolfHSM, brand new. So I'm sure it has not gone through anyone's AUTOSAR yet. But we do expect it will be once we get the rest of the AUTOSAR crypto driver set up. We would expect that people would start to bring this in as a solution.
Well, thank you so much, Bill, for hosting an informative webinar. Thanks to everyone for joining. I will email a copy of the webinar recording and PDF slides. You can keep up with our upcoming events, meet our team in person, read our blogs, and get the latest wolfSSL updates by following us on X, connecting with us on LinkedIn, and subscribing to our YouTube channel. If you have any questions at all, don't hesitate to shoot us an email at facts@wolfSSL.com. We're here to help. Thanks again, and we look forward to seeing you tomorrow on October 23rd for our FIPS 140-3 and CNSA 2.0 compliance via dual alg certs and hybrid key exchange. Have a wonderful rest of your day.